So the trapezium rule is something that you should have had a look at when you were in GCSE to estimate the areas underneath curves. This technically falls into the integration topic, but it also falls into a topic that we're going to be studying later on this year called numerical methods, because this is really not actually doing any integration here. We're trying to find out areas underneath curves without even having a clue about the reverse chain rule or substitution or anything like that. And the reason we might do the trapezium rule to find the area underneath the curve is when the curve that we are interested in is a bit of a mess, to be honest. It's too difficult to find out. What were you going to say, Rohan? No, it's much easier. Very, very, very easy. So it says sometimes finding the exact area under the graph via integration is difficult. Sometimes it's difficult to do because you can make up some functions that none of those techniques that we've done would work. None of them would work. So you may be familiar with the idea of approximating the area under graph by dividing it into trapeziums of equal width. Okay. So if I wanted to find out the area of this this section of the this yellow bit that I've got highlighted here, just wanted to point out a few of the different terms or a few of the different symbols that we're using here to say what they mean. Okay. So h, when I'm talking about h in these formulae, h is the gap between the lines that we're using. In other words, it's the height of the trapezium, hence us using the letter h. Then I use y0, y1, y2, and y3 to refer to the y coordinates for these different points along the trapezium that I have. Okay? We always start with y0, just because we do, and that's sort of like how things work in like computing and stuff like that. The first thing is always y0 rather than y1. And if we were going to figure out how we would find the area of this, the area of a trapezium, is a half a plus b multiplied by height. Or you might think of that as the average of the parallel sides multiplied by the height. So for example, this first trapezium that we've got here, you can see is a half multiplied by y0 plus y1, which is obviously this length and this length here, multiplied by h. So you can see we've got that one here. The next one would be the same, but with y1 and y2, which you can see here and here. And the next one would be with y2 and y3. So if you were to factorize all of that out, the y1 value is coming up twice, hence there being a 2 here. The y2 value is coming up twice, hence there being a 2 here. But the y0 value and the y3 value are just being left outside by themselves once because they're at either end. They only get used once during the calculations, whereas the other ones get used twice. So the area of this, if you were to try and do it as one single formula, is a half times h, which is the gap between them. And then you've got y0, the first one, plus 2 lots of the middle ones added together, plus the last one added on as well. And that should give you an approximate area underneath the graph. Yes, Mr. Kim?
So we only do 3 trapeziums?
This is just for this very particular one that I've used here. At this point, I've done 3 trapezia or trapeziums. If I wanted to make a better estimate, what could you suggest that I could do to try and make the area, the trapezium estimate become better? What were you going to say? Do more pieces, and Rayhan said I could decrease the height. So if in a question they say, how could you make your results more accurate, you could do, you could increase the number of trapeziums that there would be. You could decrease the height, have more trapeziums in there. But that would obviously be more work. So there's a trade-off between getting a rough answer and the amount of time or the amount of computing power that would be required to do something like this. Yeah, Mr. Keir?
Is there any particular reason why the first bit of the blank?
The first bit is blank.
As in why didn't you draw trapezium on the
Oh, because I'm integrating it between this value and this value. I'm not integrating it between 0 and b. I've just arbitrarily picked 2 things that I'm wanting to integrate it between. Now, sometimes the trapezium rule, they may ask you whether your trapezium rule is going to be an overestimate or whether it is going to be an underestimate. So I'm just going to draw maybe kind of an extreme sort of example here. If I had a curve that looked like this, and I did a trapezium rule from here to here and then to here, if I did a trapezium rule for this one, I would have a trapezium like this and a trapezium like this. So this kind of one would be an overestimate. How might you describe this kind of curve that the trapezium rule would give you an overestimate? It would make the area too big if you did it. What kind of curves would that relate to? Convex, good. Overestimate, when f of x is convex. When it's convex, the trapezium rule will give you too much area. It will go above it. And it will give you an underestimate when f of x is concave. And if I draw a kind of an extreme example of that, if I have something that's like this, and I do a trapezium rule, very, just 2 trapezia, you can see here, if I just did those trapezia, the area underneath it, which would be this red bit, you can see that it's an underestimate because of the nature of it being curved like that. Whereas in this case, it's going above the curve, so it would be an overestimate. So if they were to say what conditions would it be, f of x is convex or concave. Can anybody just quickly remind me though, when is f of x convex? The second derivative is greater than or equal to 0, and this one, the second derivative, is less than or equal to 0. Okay? So we're going to do a couple of examples of this. You will be pleased to know this formula is in the formula book. It's a really easy formula, but it's just one of those things. This is where I would take the formula book, because why not? Like, the other things are there to help you. The other stuff I've tried to get you to memorize is to make you feel more confident. If you're doing the trapezium rule, it's obvious you're doing the trapezium rule. You can find it in the formula book. So this is not something I would recommend you memorizing, but I do know this one off by heart just because it makes sense. Okay, it just makes sense what this formula looks like. So in your booklets, I've got this here. The general rule is the area under the curve between a and b of y with respect to x is approximately equal to the height divided by 2. We had that as a half multiplied by h, same thing. You'll notice here, at some reason, the notation has changed from y1, but whatever it means, the first value of y and the last value of y you include twice, but the middle values of y, you double all of them, okay? So we're going to very quickly do this example that we've got down here. We are approximating the region bounded between x equals 1 and x equals 3 using 4 strips. So actually, if we're using 4 strips, thinking about this for a second, 1, 2, 3, 4 strips, 1, 2, 3, 4, you're actually going to need the start value, this one, this one, this one, this one. You actually need 1, 2, 3, 4, 5 values for 4 strips. Kind of makes sense because you've got to have a beginning and an end part of it. So when we're going to do this, we want it between 1 and 3. That must mean it's going up in halves for all of that. And it's a very, very simple one that we're doing here. We're going to be squaring all of them. So that squares to 1, that squares to 4, that squares to 9. 1.5 squares to 2.25, and 2.5 squares to me getting my calculator out because my brain's too slow this morning. 6.25. So if we were going to work out what the area of this is equal to, we could say that the integrating x squared with respect to x between 1 and 3 is roughly equal to the height of these strips, which is 0.5, divided by 2, taking it from here. Then we're going to have the first and the last one. Instead of writing the last one at the end, I just always do the first and the last one to begin with, plus 2 lots of the middle ones. So you get 2 lots of 2.25 plus 4 plus 6.25, close off the brackets, and we get what the area is approximately equal to. So that then just requires you to do all of this in your calculator. So what have I got here? That's 0.25 multiplied by 10 plus 2 times 2.25 plus 4 plus 6. So
What you mean the 1.5?
So all I did to get these is I just squared them because the function that we're looking at is y equals x squared.
The 0.5.
Oh, because the 0.5 is the gap between each of them, is h, from this bit that we've got here. So when you type all of this into your calculator, if I've done it correctly, I believe it should be 8.75. Now, we obviously can integrate x squared between 1 and 3. What do we expect this to be, though? Do we think this is going to be an overestimate or an underestimate?
Because x squared is like that. No question.
We think this is an overestimate because if you think about what an x squared graph looks like, it looks like this. It is convex. So I'm actually just really quickly going to integrate between 1 and 3, x squared with respect to x. In fact, why don't we just do it on our calculators to save us doing any kind of substitution at all?
It's
8.66 or 8 2/3, is it? 8 and, okay, let's just do it like you said, 8.66 to 2 decimal places. So yeah, it's an overestimate because of the shape of the graph, but it's sort of close, so it's useful. If I wanted to make it even closer, instead of going 1, 1.52, 2.53, I could maybe go 1, 1.1, 1.2, 1.3. It'd take a lot longer, but it would give me a pretty good estimate of what the thing should be looking like, okay? So we want to think about how we might be able to do this a little bit quicker. I've got an exam kind of question that we've got here. This is what it might look like in an exam. It might say, complete the table below with the value of y corresponding to x equals 1.3, giving your answer to 4 decimal places. Now, you should know how to do this better than I can, but your calculators can actually generate whole tables of values. And I'm looking to probably people like Hamza, who's normally very good with the calculator. Pardon?
I think it's on mode menu 9.
On those ones. Okay, so when you do menu 9, you can then type in what the function looks like, and it can then generate what the whole table of values should look like for you. But I'll come and I'm going to have a look at that in a moment and see if we can do that. But for this one, just need to type in 1.3 into this particular function that we've been given. So it'll be 1.3 over the square root of 1 plus 1.3. And to 4 decimal places, it is 8.572 to 4 decimal places. But you can, on your calculators, do these tables of values. It then asks you to do the trapezium rule with all the values of y in the completed table to obtain an approximate value for this particular thing that we've got here, giving your answer to 3 decimal places. And it says you must show clearly each stage of your working. So you do need to write out what that first line looks like. But after that, you can just type it into the calculator. So what's our value of h in this particular example that we have here? 0.1. So it's going to be a 0.1 over 2. And we then have the first plus the last plus 2 lots of the middle terms. Done. So we should end up with, to save me time writing all of that out, you've got your 0.1 over 2. You've got your first one here, your last one here, and you've got 2 lots of the middle ones, and you come up with 0.416. Yeah.
Just a question. If we were doing the trapezium rule with x squared, but we were doing it between like x is minus 3 and x is minus something else, would it still be overestimate?
Well, actually, if you think about what the x squared graph looks like, it is always convex. The shape of it is always convex. And that's because the second derivative of it is always positive. Is that right? X squared, 2x. Yeah, it always will go to 2. So no matter where you are on the graph, it's always going to have that slight bend to it. So when you do the trapezium rule, it's always going to be an overestimate. But there will be some graphs that are convex for some of it, concave for some else of it. And so the trapezium rule, we don't know if it's necessarily going to be an overestimate or an underestimate. You'd have to actually work it out by doing it properly and then see either way. Okay?
So where did the 0.1 come from?
The 0.1 comes from the value of h. H is the gap that goes between them. If you remember in the formula that we've got here, h is the width of those trapeziums. It's the width of each strip that we've got. So we can see here it's going up in 0.1. Okay? So we're going to do one more example, and then we are going to do a little bit of practice. But there's nothing, hopefully there's nothing difficult with this. If you get a trapezium rule question, it's great. The way the trapezium rule question came up in the exam in 2019, last summer, is they did it like a mechanics question where they said it was like the speed of an aeroplane at certain times in a table, and you had to work out the distance it had travelled, which was trying to integrate underneath it, and you had to try and work out its trapezium rule. Even the trapezium rule they made hard. That exam was horrible, horrible. Okay, so this is the classic kind of way that they like to do these questions, and then you're just going to do practice after I've done this one here. They've said, given that I, they often use I to say what the integration thing is equal to. Given that I is equal to the integral from 0 to pi over 3 of sec x dx, we want to find out what the exact value of I is. Now, sec x is one of the functions that I don't believe I've asked you to memorize. I think actually this is one that's in the formula book that's going to be helpful for you to do. So if you actually look in your last few pages of the booklet here, I believe I've said about how you integrate sec x.
Can you just do what? Learn of codes.
No. Have you found it in the last pages?
Yeah.
Yep.
Plus tan x.
Ln of sec x plus tan x is what it integrates to between 0 and pi over 3. Shh. So that is going to be the ln of, well, sec of pi over 3 is 1 over cos of pi over 3, which is 2. So that's sec of pi over 3. Let's just do this slower. Sec of pi over 3 is 1 over cos of pi over 3. If you put that in your calculator, it ends up as being 2. Tan of pi over 3 is root 3. Sec of 0 is 1 over cos of 0, which is 1. And tan of 0 is 0. What's the ln of 1? 0. So this is all equal to the ln of 2 plus root 3. That's part A of the question. And it might be useful to work out what that is as a decimal, just because we know we're doing some trapezium rule here. So it's 1.316957897. Then it asks us to use the trapezium rule with 2 strips to estimate I. So we're going to have to draw a table for part B. We've got what
0.
x is equal to, and then what sec x is equal to. We're going to use 0, pi over 6, and pi over 3. So we're then going to have sec of 0, sec of pi over 6, and sec of pi over 3. In fact, I could probably work these out. So sec of 0 is 1 over cos of 0, which is just 1. 1 over cos of pi over 6 is 2 root 3 over 3. And the other one is 2. So I is approximately equal to, what's the value of h for this trapezium rule?
2 root 3 minus 3.
No. Pi over 6. It's going up in pi over 6. So it's going to be pi over 6 over 2. And then you've got the first one plus the last one plus 2 lots of the middle ones. So that's pi over 6 over 2 multiplied by 3 plus 4 root 3 over 3. And you get 1.389997991. So it's kind of close, but kind of not close either. I'm not sure if I can be bothered to do part C, which says to do the trapezium rule with 4 strips to find a second estimate of I. But what do you anticipate the answer to be?
More accurate.
More accurate.
So less than that.
So less than that, much closer to the one that I've written in red. But I will bother doing part D. I'm not going to bother doing part C, but I will bother doing part D, which says find the percentage error in using each estimate. So we're imagining that the part C percentage error is going to be lower, but we'll do the percentage error. Does anyone remember how you do percentage error?
The estimate you get over the actual number you get times 100.
You have to do the difference between them. So you would have to do 1.389997991 minus this one, ln 2 plus root 3, all over ln 2 plus root 3 times by 100. And the formula that's really coming from is it's the change over the original or the actual multiplied by 100. Sometimes the original one is the actual value. So if I put that one in the calculator, let's do minus ln of 2 plus root 3 divided by ln of 2 plus root 3 times it by 100. So the percentage error is 5.55% to 2 decimal places. Okay? We have got 15 minutes to just do a few of these practice questions from the exercises, but hopefully this is A, familiar, and B, easy. Okay, so this is a nice topic because it's just like, cool, it's pretty straightforward. So I'm just going to grab a couple of questions from that booklet that you guys can have a go at for me.